Okay, I wanted to set up an example problem for you. I actually made this video already. However, my mic was accidentally muted, and so there's no sound. So what I'm going to do is I'm going to go back through this and go through the steps that I went through. So first off, let's look at the problem here. So we want to establish the number of days it takes a dealer to sell a car, and essentially the average number of days. So we take a random sample of 50 cars, and we find that they spend a mean time on his lot of 54 days. So I guess he sells a car on average in 54 days. Let's assume, so point estimate here for this would be 54. But let's do it. What we want to do is an interval estimate. So first things first, we need to have some more information, and that is we assume that the population standard deviation for this sort of thing is 6 days. Okay, come down here. Let's fill in this information here. So I erased some of these things so we could fill them back in again. So see if you can pause and fill in the information for the statistics and parameters that we need to do this problem. Okay, let's go ahead and do this. So n, our sample size, actually is going to be 50 cars. And our sample's average was 54 days. The standard deviation was a population value. It had a value of 6. And the population mean we don't know. That's what we want to try to determine. We want to do that with 95% confidence. So if you look over here at the right, what we want to try to do is we want to try to do that with a 95% confidence. So we want to set up a 95% confidence interval around this value. And that's going to lead to a z value, z sub alpha over 2, where alpha here represents 5%. So alpha over 2 is 2.5%. So that's why this is z sub 0.25. That's 2.5% and written in decimal form. Well, we already showed you, I already talked about it up above in the last video, that the z is always going to be equal to 1.96. So this z is going to equal 1.96, and this z is going to equal minus 1.96. Okay? So let's take all these values and stick them in our relationship for confidence intervals. So that relationship is here. So we take x bar, we subtract z times sigma over square root of n. That's less than our population mean, which is less than x bar plus z times sigma over square root of n. So now take the values up here, pause the video, plug them in here, and see if you can get the 95% confidence interval for our mean based on the data that we took in our sample set. Okay, so going to continue on. So for x bar, we stick in 54. For z, 1.96, this is a negative here. For sigma, we got 6 over square root of 50. That's less than our mean. And 54 plus 1.96 times 6 over square root of 50 is greater than our mean. So our mean is nested between these two values. So if you want to do the calculations, come back. So you'll have 54 minus 1.7 is less than our mean. 54 plus 1.7 is greater than our mean. So our mean is between those two numbers. And if you calculate that out, that means the mean is between 52.3 and 55.7. Another way to write that is 54 plus or minus 1.7. And again, this value here, this z sigma over square root of n, is our margin of error. Okay, now a 95% confidence interval is just one of many typical confidence intervals that people are often interested in determining. We could also do a 99% confidence interval. Or we could do an 80% confidence interval. 80% is a smaller area than 95. 99 is a larger area. But again, we would need to figure out what these z values are. Z1 and Z2 for each of these. Same here. We need to figure out what Z1 is and Z2 is. We could use the same equation, but we're going to have to figure out what a new Z is. So, in this situation, with 80, alpha equals 0.2. So alpha over 2 equals 0.1. In this situation, alpha equals 1%, or 0.01. That's what's left over after you take 1 minus 99. That's how much area is in these two tails, 1%. So the area in one of these tails, alpha over 2, which is really what we got to use to figure out what z is 0.005. When we do this, we're always going to come up with the same z's. So z of 0.1 is 1.28, and z of 99, well, it's not 99, it's the complement of 99. Z of, it's half the complement, 0.05 is approximately 2.58. 2.576 is probably the number you're going to get for a 90%. Z I see a small little correction I want to make over here. Trying to erase. This should be 0.05, because this is going to be alpha equals 0.10. So alpha over 2 equals 0.05, half of that. So z of 0.05 then is approximately 1.65. So it's not necessary to go and look this stuff up on your z-tables all the time, because these numbers are always going to turn out to be the same. You just know that if you're going to do a 95% confidence interval, z is going to be equal to what we displayed before, 1.96. If you do a 99% confidence interval, z is going to be equal to 2.58. A 90%, z is equal to 1.65, and 80% z is equal to 1.28. So let's do an example. Second example. Okay, I wrote the problem down to save some time here. A store found it averaged 362 customers an hour. Assume that the standard deviation for the population is 29.6, and that the store, to find the 362 customers an hour average, used a sample of 40 hours. Find a 99% confidence interval for the population mean. Okay, take a second here and fill in these values here. We're going to need them to calculate our confidence interval. Okay, so Did you get this for sigma, for x, or for x bar? For x bar, our average was 362, and n was 40 hours. So population was 29.6 hours, our population standard deviation. And for the population mean, well, we don't know that. That's what we're trying to figure out. Okay, next, we got to figure out what z is. Z alpha over 2 equals z. So in this case, it's always good to draw a picture. In this case, we're talking about a 99%. That means on opposite sides, alpha equals 1%. So in decimal form, alpha equals 0.01. Alpha over 2 equals 0.005. So z equals 2.58. We can actually see it up here for these values. So scroll up if you need to. Meanwhile, I'm going to continue. So here's the relationship we're going to use. X bar. I'm going to put it in this form. Plus or minus z alpha over 2 times sigma over square root of n. This is what our mean equals. So I'm writing it a little differently than I did up above. But you'll see it's some sample value plus or minus our error equals mu. Try to fill in these values now from the data we have up above. So x bar equals 362 plus or minus 2.58 times 29.6 over square root of n. This is a little more compact. That's why I like to write it like this. Okay, let's put in what n actually is here, which was 40, and do our math. So we get 362 plus or minus, do the math here, give you a second, 12.1 equals mu. So mu, and we could leave it like that as our answer, or I could go, I'm going to go ahead and indicate this, or I could go and I could figure out what this is, add and subtract 12.1 from it, and write it this way. So 362 minus 12.1 is less than mu is less than 362 plus 12.1, which is 349.9 is less than mu is less than around 374.1. Okay. So that's our so we're 99% confident that our population mean falls between 349.9 and 374.1. I'm going to end here.